Imagine standing beneath a velvet night sky, a canvas of twinkling lights stretching endlessly above you. Among those countless stars, one burns with a fierce reddish glow, commanding your attention like a cosmic beacon. This is Betelgeuse, a red supergiant in the shoulder of Orion, a star so massive, so luminous, that it has captivated humanity for centuries. Its name, derived from Arabic, hints at its prominence: the hand of Orion, or perhaps the armpit of the giant. To the naked eye, it's a fiery ruby in the heavens, but to astronomers it's a living enigma, a stellar titan whose recent antics have set the scientific world ablaze with curiosity and wonder. Betelgeuse is not just a star, it's a window into the universe's grand narrative, a story of birth, transformation, and cataclysmic rebirth that connects the iron in your blood to the explosive hearts of dying stars. In 1929, humanity's understanding of the cosmos underwent a seismic shift. Edwin Hubble, peering through the great telescopes of his time, discovered that the universe was not a static, unchanging expanse, but a dynamic, expanding arena. His observations of galaxies, their light stretched into redder wavelengths, revealed that they were racing away from us, as if the fabric of space itself were stretching. This revelation, now known as Hubble's law, laid the cornerstone for the Big Bang theory, forever altering our perception of the universe. It was no longer a timeless vault but a living, evolving entity, shaped by forces so vast they defy comprehension. By the mid-20th century, scientists had built on this foundation, unraveling the intricate processes that forge the elements of life itself. The stars, they realized, were not just distant lanterns but cosmic crucibles, where the fundamental building blocks of existence, carbon, oxygen, iron, were crafted in nuclear fires. Consider the atoms that make up your body: the calcium in your bones, the oxygen in your breath, the iron coursing through your veins. These elements were not born on Earth. They were forged billions of years ago in the hearts of ancient stars, under conditions of unimaginable heat and pressure. This process, called nucleosynthesis, is the universe's alchemy. In the cores of stars, lighter elements like hydrogen and helium fuse to form heavier ones, releasing energy that powers their brilliance. As massive stars age, they progress through a sequence of fusion stages, creating carbon, oxygen, and eventually iron. But iron is the end of the line. When a star's core fills with iron, fusion can no longer sustain the outward pressure needed to counter gravity's relentless pull. The result is a catastrophic collapse, followed by a supernova, a violent explosion that scatters these elements across the cosmos. These stellar— You are, in a very real sense, made of stardust, a child of the cosmos linked to the life and death of stars like Betelgeuse. Betelgeuse, with its staggering size and luminosity, is a prime example of this cosmic drama. If you placed it at the center of our solar system, its outer layers would engulf Mercury, Venus, Earth, Mars, and stretch beyond Jupiter's orbit, swallowing entire worlds in its fiery embrace. Despite its immense scale, it lies just 640 light-years away, a mere hop in cosmic terms, yet a distance so vast that light from Betelgeuse takes over 6 centuries to reach us. If you could travel at the speed of light, a feat far beyond our current technology, it would still take 640 years to arrive at its doorstep. With today's propulsion systems, such a journey would span millions of years, a testament to the vastness of the universe and our place within it. For generations, Betelgeuse has been a familiar landmark in the night sky, its reddish hue and brightness making it one of the most recognizable stars. But in recent years, it has transformed from a steady beacon into an astronomical celebrity, its behavior sparking fascination and debate. Since late 2019, Betelgeuse has exhibited dramatic fluctuations in its brightness, including an event so striking it's been dubbed the Great Dimming. During this period, its brightness plummeted, dropping to a level that made it noticeably fainter to the naked eye. To astronomers, this was no mere curiosity. It was a clarion call, a signal that something profound was happening within this aging giant. The dimming, which saw Betelgeuse's V-band magnitude fall to around 1.61, ignited speculation that it might be on the cusp of a supernova, the explosive finale that awaits all massive stars. While that theory remains unconfirmed, the event underscored Betelgeuse's instability and galvanized a global effort to study it with unprecedented scrutiny. Betelgeuse is a pulsating variable star, meaning it naturally expands and contracts in cycles that affect its brightness. When it swells, it emits more light, appearing brighter in our skies. When it shrinks, its light dims. Scientists have identified two primary cycles, a shorter one lasting about 185 days and a longer one spanning roughly 2,300 days. These pulsations are driven by the star's internal dynamics, as its outer layers respond to the energy bursts from nuclear fusion deep within. But the recent changes have deviated from these predictable rhythms, showing variations in magnitude and timing that defy simple explanation. The Great Dimming of 2019 to 2020 was particularly dramatic, prompting astronomers to train their most advanced instruments. Telescopes like the European Southern Observatory's Very Large Telescope, NASA's Hubble, and the James Webb Space. As a red supergiant, it sheds material at an astonishing rate, equivalent to several Earths' worth of matter every year. This material, expelled through powerful stellar winds, cools and condenses into vast clouds of gas and dust. During the Great Dimming, astronomers believe such a cloud may have formed in our line of sight, temporarily obscuring Betelgeuse's light. Infrared observations, particularly from NASA's now-retired Spitzer Space Telescope, detected excess emission consistent with freshly formed dust, lending weight to this idea. Another factor is convection, the churning of hot plasma from the star's interior to its cooler surface. Betelgeuse's convective cells are colossal, some potentially larger than Earth itself. Variations in their efficiency or organization can cause dramatic shifts in brightness, creating the erratic behavior we've observed. To unravel these mysteries, astronomers employ a suite of sophisticated techniques. Photometry tracks changes in brightness over time, providing a detailed record of Betelgeuse's pulsations. Spectroscopy, meanwhile, dissects the star's light into its component wavelengths, revealing its chemical composition, surface temperature, and the radial velocity of its outer layers, how fast they move toward or away from Earth. These measurements show that Betelgeuse's atmosphere is a turbulent, dynamic place, roiled by shock waves and mass ejections. Complementing these observations are computational models that simulate the star's internal structure, incorporating complex equations of convection, nuclear fusion, and stellar dynamics. These models suggest Betelgeuse is in a late stage of evolution, likely fusing helium into carbon or even heavier elements like oxygen or neon in shells around its core. Each fusion stage brings it closer to its inevitable end, a supernova that will mark its final act. The prospect of Betelgeuse going supernova is what truly captures the imagination. When that moment comes, and it could be tomorrow or in 100,000 years, a blink in cosmic time, the star's core will collapse under gravity's unyielding grip. Unable to sustain fusion, the core will implode in seconds, triggering an explosion of unimaginable power. The supernova will blaze with such intensity that it could outshine the full moon, casting shadows at night and remaining visible even in daylight for weeks or months. Historical records tell of similar events. In 1054, a supernova in our galaxy created the Crab Nebula, so bright it was noted as a guest star visible during the day. Betelgeuse's explosion would be even more spectacular given its mass and proximity. Yet, despite its brilliance, a Betelgeuse supernova poses no threat to Earth. At 640 light-years, it's far enough to be safe, unlike a closer explosion, which could unleash gamma-ray bursts capable of damaging Earth's ozone layer or electromagnetic pulses that might disrupt satellites. Instead, Betelgeuse's finale will be a cosmic spectacle, a rare chance to witness the death of a massive star in real time. After the explosion, its core may collapse into a neutron star or, if massive enough, a black hole, a gravitational abyss emitting radiation from its accretion disk, offering scientists a natural laboratory to study extreme physics. Beyond its individual drama, Betelgeuse is a key to understanding red supergiants, a critical phase in the evolution of massive stars. These giants are rare, their immense size and turbulent atmospheres making them challenging to model. Betelgeuse's proximity allows astronomers to study processes like convection, pulsation, and mass loss in unprecedented detail. The star's surface, churned by convective cells like slow-moving currents of molten plasma, reveals the chaotic interplay of heat and gravity. Infrared and ultraviolet observations track the dust and gas it sheds, enriching the interstellar medium with elements that will one day form new stars and planets. This cycle of creation and destruction is the heartbeat of the cosmos, linking Betelgeuse's fate to the broader story of galactic evolution. Astronomers have also considered whether Betelgeuse might have a companion star, a binary partner that could influence its behavior. In binary systems, stars can exchange mass, altering their evolution and potentially accelerating fusion processes. While no definitive evidence of a companion exists, the possibility adds another layer of intrigue, prompting researchers to refine their models of massive star evolution. Meanwhile, the Great Dimming and other recent changes have transformed Betelgeuse into one of the most studied stars in the sky. High-resolution images from the Very Large Telescope reveal its surface in stunning detail, showing vast, shifting patches of brightness. Spectroscopic data track the motion of its atmosphere, while computational simulations explore the complex interplay of fusion, convection, and rotation within its core. The uncertainty surrounding Betelgeuse's timeline to supernova only heightens its allure. Stellar evolution models are notoriously complex, with small changes in temperature, rotation, or composition leading to vastly different outcomes. Three-dimensional simulations, incorporating turbulent convection and magnetic fields, suggest Betelgeuse is in a transitional phase, but the final leap to iron core collapse remains unpredictable. When it happens, the supernova will not only dazzle our skies, but also enrich the cosmos, scattering heavy elements that may one day form new worlds. It will be a testament to the universe's endless cycle of birth and rebirth, a reminder that even in death, stars give life. Betelgeuse's story is more than a scientific curiosity. It's a profound reminder of our place in the cosmos. Every atom in your body, every breath you take, ties you to the stars. As we watch Betelgeuse pulse and dim, we're witnessing the universe's ongoing narrative, a tale written in light, heat, and the raw materials of existence. Whether it explodes in our lifetimes or long after, Betelgeuse will leave an indelible mark, a brilliant farewell that illuminates the sky and our understanding of the universe's vast, interconnected dance.